Welcome to the Cosmic Pie Podcast, Episode 14, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live here from the campus of the University of North Dakota.
Yep.
We do have a chat feature that's running, so if you have any comments or questions that you'd like to ask us during the podcast, please feel free to use that feature, and we'll try to answer the questions as best as possible.
Yep. I mean, as long as they're reasonable questions, preferably on topic, things like that.
Even if they're not quite on topic, if we have time, we'll definitely get to them.
Yeah. If we have time, that's the other thing. Yeah.
Just like we know some stuff, but we're an expert in nothing.
I don't know about that either. I don't know I can go that far.
So, whatever answer we give you.
That leads into our disclaimer. The answers we give you and the opinions we express are those of myself and Wayne, not those of the university or the Department of Physics and Astrophysics or any other entities, just us, folks.
Yeah, you know who to blame.
You know who to blame.
Don't blame it on the rain, just blame it on us, right?
All right, Millie. Does that mean
Millie Vanilli?
Blame
so we're not really talking, we're lip syncing. Someone else is talking behind us.
Right.
Okay, so what we'll do at the beginning, we'll kind of do an update. And I wanted to update everybody on the comet that's visible or sort of visible in the morning sky. So this is Comet Swan, F2. One of the things that last week we talked about this, or certainly a week before that. Week before that. So this comet is, well, it was at a brightness level that placed it such that you couldn't see it with the unaided eye. You needed a telescope, or a pair of binoculars is the best for viewing comets like this. It had a fantastic tail. I've seen some early images of it.
Long tail,
and the comet arose a little bit before the sun. So there's like the sweet spot before the sky gets too bright, and a point in which is dark enough that you can see the comet. And you got to be careful anytime you're scanning around near the place where the sun is rising, and you have a pair of binoculars. Of course, you don't want to venture too close to the sun with that. The interesting thing that happened, so from North Dakota, at least from Grand Forks, I've been waiting since the news came that this comet was available to be seen, waiting to get a good view of it. And of course, the weather didn't cooperate. It seemed like even on a night where it was relatively clear at the beginning of the night, by the time we got to like 3 a.m., the clouds rolled in. And you have to wait till after 6, essentially, to see this comet. It literally is just when the sun is rising.
I was about to say, that's close to sunrise here.
Yeah. And so I never found a good day in which I could look for it. But unfortunately, a couple days ago, it was reported that the comet lost its tail.
Yeah. How does a comet lose its tail?
Well, it disconnects there's an outburst of material. Then if that outbursting shuts down, there's no more supply of material that comes from it, right? The sublimation process has finished on its surface. And then comets can lose their tail. They will disappear if you don't have any more outgassing of the material from the head of the comet itself.
Right.
So the comet has a head, the coma part of it, but it no longer has a visible tail. And because of that, of course, the overall brightness of the object declines, making it very difficult to see, especially the fact that you're fighting the light coming in the daytime, right? The dawn approaching. So
this is the problem with predicting what comets will do, and why you've probably heard Wayne and I scoff a little bit when they start talking about how bright a comet's going to get. You just never know. You really don't. Like I remember back in the early 2000s, 2010-ish, 11-ish, there was Comet Holmes, I think it was, that they just, it's going to get so bright, and then it just completely broke up. And so the brightness went from brightening to just nothing.
Now, before my time, right, there was Comet Kohoutek, I guess, that the public media went on about, right, in terms of it was going to be extremely bright and stuff. But the classic one is Comet Halley in 86.
Yep.
And from the northern hemisphere, it wasn't a good sight at all. It was very, very low in the sky. I remember looking at it as a young kid through my telescope, and it was really low, almost right on the horizon.
Right.
And so it was very, very difficult to see. If you're in the southern hemisphere, of course, it's a lot better. It was higher up in the sky. So it wasn't a great pass for Comet Halley. But you got to wait 76 years for it to go by again.
So you go out and you see it.
Yeah, so we just gone past the point of its furthest point of its orbit from the sun, it's aphelion.
Yep.
So now the comet Halley is inbound. We just
Just got to hang in there.
with advancements in modern medicine,
It could
and
happen.
eat a whole food plant-based diet and stay away from fast food and ultra-processed meats. All the good things.
All the good things that make
taste
life
good, I should
enjoyable.
say. They may not be good for you, but they taste good, unfortunately. Why do they do that, Robert? That's a mystery of the universe. Why does all the bad food taste so darn good?
Because we're hardwired to look for salty, fatty, sweet things. So
Box of donuts or a bowl of lettuce? Those decisions are hard to
donuts, kale.
Anyways, if you can live long enough, you might see the next pass of Comet Halley. But of course, you don't have to wait that long. Comets pop by at random times, such as this one. You never know. Maybe by this summer, we'll have a good comet that'll
We'll
be
have a good
visible
one. Yeah.
for the Northern Hemisphere. We'll keep our fingers crossed on that. But you never know. So this one seems to be done its thing for us. And we're not going to have a good view of it anyways.
Right.
And so that'll be the
Which
end
is
of it.
unfortunate.
Which is unfortunate.
They're nice to look at.
Now, if you do have a large telescope, of course, things are different, but they're still very difficult. The way it's going outwards on its trajectory, it's very close to the sun direction, and so you take an awful chance. I'd rather not look at the comet than risk, damaging your eyes.
Right. So, I mean, these pictures are indicative of what you're going to see even through a telescope anyway.
Yeah, well, that's it, right? I mean, nowadays, of course, with large telescopes, they're all geared up. You just put in the coordinates, right, essentially declination.
Right.
Right? You can slew to that location, keep the cover in front of the telescope on, and then once you get to where the comet is, then remove it.
Right.
So you don't accidentally,
Sweep across the sun.
Yeah.
I have burned a patch of my hair. I've not told you that story. I
No.
think. I was had a 16-inch telescope that I'd put a 4-inch baffle on, so it was like its lid, but a 4-inch aperture solar filter.
Yeah.
And I forgot to cover the finder scope.
Oh.
So I was looking through the eyepiece and started going, something burning. Ow! Caught my hair on fire. So,
Wow.
yeah. So you see, we do dumb things too.
So imagine what it would do to your eyes, you see.
That's it.
You want laser surgery? Here, it's free.
It's free.
If you have like a retina that's detaching, we'll reattach it.
You won't see anything, but it'll be attached.
Yeah, I shouldn't laugh about that. I always tell people stay away from the sun. Don't even attempt to do it, just in case, right? Don't even, some people do that, and it's like, no, don't ever do that. It's
And
not
definitely
worth it.
do not trust any eyepiece filter.
Yes, solar filter in the eyepiece.
If solar filter needs to be at the front of the telescope, not at the eyepiece, you want to block all that energy from getting into the system.
That was a standard in small telescopes.
Yes,
I
it
won't
was.
mention the brand. You might get sued or something, but they would have the little solar filters that you screw on at the end of the eyepiece. There was threads
Yep.
all set up to go. And even if you drop one, if you accidentally crack it, a hairline crack, and then you put your eye to that,
Your eye is toast.
taking an awful chance.
Literally.
Even the mylar filters we put in the front of telescopes, I'm uncomfortable with that. I'd rather project the sun on a screen and look at like the sunspots and stuff.
That's yeah.
So then you're guaranteed you're not gonna
I
cause
like
any
the
damage.
glass plate ones myself. So.
Yeah, you always have to be careful.
Absolutely.
Anyways, moral of the story: never look near the sun or at the sun. Obviously, with any optical device at all, whether it's even a small, low-power binoculars, you can do permanent damage to your eyes.
Yes.
And right now, we don't have the technology to take your eyes out and put new ones in there and make them function just as well. Maybe in the future we'll have that, right? AI can do the surgery.
Right.
Did you see that was on the news lately where AI was
Yes.
doing? Did you see that?
I saw that.
It's amazing. So
Yep.
the advancements in medicine like that.
Uh-huh.
So it controls the robot that does the surgery, and the recovery time was a lot less than what it would took like a human being to open up even further, right? A bigger wound, I guess, right?
Bigger wound and
Bigger incision.
less precision.
Yeah,
I mean, that's what machines are good for, is repetitive patterns and high precision.
yeah. So it'll be interesting where that goes in the next several decades for sure.
Absolutely.
Now the big news in astronomy in the
Oh, Lordy,
last
here we go.
7 days, and I've noticed this was like late last week, so just before the Easter weekend kicked in, And this was the news of a detection, possibly, quote unquote, of what they call, and I'll get it right here, dimethyl sulfide.
Or dimethyl disulfide.
Or dimethyl disulfide from the spectrum of an exoplanet atmosphere taken with the James Webb Space Telescope. Now, I cut the title page of the paper just to let people know this is not just like a press conference or some kind of news leaked out. It's actually a paper that has been submitted for publication in a peer-reviewed journal, and a good one,
Astrophysical Journal, AJ.
It's one of the higher-ranked journals in our field, close to the highest rank. So this is about observations. It's actually, there's a little bit of a history here. So in the past, there has been observation of this particular star, and this star is about roughly 124 light years away in the constellation Leo, for those who are interested in those sort of things. And there were observations taken a little while ago, a little over a year ago, of one of the exoplanets that's orbiting this star. Now, the exoplanet itself is a lot larger than the Earth. It's like super Earth. It's about nearly 9 times the mass of the Earth itself, which puts it about 2.6 times as large as the Earth. And it's one of those planets where we think that it is covered in water, like the water world from that movie. Kevin Costner.
Yep, called Waterworld.
Yeah, except in this case, it would have mainly a lot of hydrogen in its atmosphere. So it's a hydrogen-rich atmosphere in this sort of water world. And the spectrum that was taken, and we even said stuff on the podcast.
I think we've talked about it.
That there was a hint of the detection then of this dimethyl disulfide and the dimethyl sulfite.
And I will point out that it also has been detected as methane and carbon dioxide. Now, those are less impressive because methane, Uranus and Neptune have a good quantity of methane in them. And CO2 is everywhere.
Right. Now, these two chemicals then were detected using one of the instruments on the James Webb Space Telescope, but the detections were not robust. Right. Were low signal to noise, in other words. So you didn't really know if it was there or if it was sort of buried in the noise. Now, what's profound about these two molecules is that they are produced readily by biology.
Biological activity, yes.
So life forms can produce these chemicals.
And if I'm not mistaken, they're readily broken down by photonic means, by light from the parent star. So they're not going to linger if they're not being constantly replenished.
Bingo. They don't last very long. Now, what these researchers did is they went back to James Webb Space Telescope, put in another proposal, got time on a different instrument, one that is more sensitive, and took better observations. So what they are showing now is essentially then the spectrum of the same planet that they were looking at before, but now the detection, both of the dimethyl sulfide and the dimethyl disulfide is more secured. It's more robust. Now, how robust? Well, we'll see that in a second.
Yep.
So here is the spectrum, and what you have here, and this is how this game kind of gets played. You look at the spectrum. In this case, it's absorption line features. So the light then that passes from the sun through the atmosphere of the exoplanet, the atmosphere will imprint signatures on that spectrum that's conducive to the material in which that atmosphere on that planet is made up of. Okay? So if the planet is on the other side of the star relative to us, we're not going to be able to see it, and it has no effect on the spectrum of the host star. So at that point, you can get a spectrum of the star itself.
Right.
Once the planet, the exoplanet, comes in front of the star relative to us, then the light, some of that light passes through the atmosphere of that planet. And it can, if it absorbs enough, then that signature can be seen with sense enough instrumentation.
Right. I've got a nice little graphic of it. It's a little messy, but due to having to change the aspect ratio. But basically, if the planet is in the way, it's going to block all the light. Whereas if the atmosphere is in the way, it's going to absorb some of the light depending on what materials are in that atmosphere. So looking at that, that's what this is. We then subtract what we know, the stellar spectrum, the host star, what its spectrum is, and whatever's left must be the imprint of the atmosphere.
And these are all done through radial velocity measurements.
Mm-hmm.
So that means the star then is going to be, if you like, moved a bit towards us. If the planet is on our side of the center of mass, tugging the star towards us, so the light is shifted a little bit towards the shorter wavelengths, blue shift. And then when the opposite extreme happens, the planet's on the other side relative to us, then the star is pulled in that direction a little bit away from us. So then the lines are all shifted to longer wavelengths, so we have the red shift.
Right. And so you've got to factor in correct for all of that. And in the end, you try to model the spectrum. And if I'm reading this graph correctly, the black line through the middle of that blue bar is the actual spectrum. And then the blue is a model that they've applied to it. And then the yellow dots are, of course, the data with their error bars.
So the black line is just a standard fit to the blue model.
Oh, okay.
The data points is the yellow dots there with the uncertainties. So you just take away the blue region, take away the black curve that goes through the middle of it. You just have those yellow dots. Now, what does that represent? You see?
It could be just about anything.
You know the wavelength.
You know the wavelength.
So you can think of what are things in the atmosphere of the exoplanet that would cause the dips in
the absorptions
in
at
the
those
light, in the
wavelengths.
brightness.
Yeah. Because that's what the y-axis is the amount of light that's absorbed at those wavelengths. So the lower they are, the closer down to the x-axis, the darker it is there. And the further up they are, the brighter, less absorption. So basically you can see what wavelengths it's darker at and which ones it's brighter at. And that, of course, is the spectroscopic signature of what it's passed through.
And the problem with this is you're working at the extreme limits of the instrument on this. So notice the large uncertainty on the relatively large uncertainty on the data points, especially when you go to much longer wavelength.
Now, why does the uncertainty increase with wavelength like that?
Because that's effect of the sensitivity of the instrument itself. So the signal to noise is not as efficient at those long wavelengths as they are at the shorter wavelengths. So the signal to noise is a lot less at the right side of the plot than it is on the left side of the plot. And that factors in and so there's a couple things that would affect that. Number one, on the right-hand side of the plot, there's some interesting features. You're just not going to puzzle out through those data points. Right. The uncertainty is just too large. So given the data that you have here, what are you going to do with it? Well, if you go on the left half of the plot, notice the uncertainty is a lot less, and that's good because you can start to see some of those absorption features due to the various molecules. Right. And the reason why we keep saying that it's dimethyl sulfite or dimethyl disulfite is because we can't really distinguish the two. Right. They're pretty close together in terms of their absorption features. And it could be a combination of both in the atmosphere anyways. Right. So you're looking at sort of the composite spectrum in that case.
Okay.
So, and thinking about what the overall spectrum is, here is a plot, a figure that shows basically the absorption line features that you would see due to different molecules. So we have methane, CH4, the red curve. Then the next one to the right of that is carbon dioxide. Then we have these two dimethyl molecules. And if you just look at those, right, so it's sort of the blue curve and the purple curve, you can see where they lie in terms of the wavelength coverage here that goes from, a little bit shorter than 6 microns all the way up to about 12 microns. And notice there are places where they're very similar, but there's also places where they are very dissimilar.
Yes.
So to puzzle out these, you have to look at regions where you can possibly see the difference of it. But unfortunately, the places where they are dissimilar the most, that's sort of on the right side. That's where the data is the crappiest,
the
right?
sensitivity is the lowest.
Yeah, the signal to noise is a lot less there, so that makes it bad to discriminate between the two.
I will say, this is one point where, just to use the buzzwords, this is one type of analysis that can be done by AI probably
Yeah.
better than humans because they can recognize those dips a lot faster and quicker than we can.
That's exactly right. If you take just these
Pardon,
four
folks.
molecules and you combine them together, that's the black curve that you get there, the combined curve. But that's not the observation. That's just if you take the individual molecules, right, to
Yeah.
as high as resolution you want, because they're models, and you
Right.
add them, sum them together, then the black curve is what you get. But the data points, if you go back a slide,
Okay.
once again, is where those yellow data points are. Those yellow points are. That's the data from the instrument itself.
Right.
So it's not that clean. So
and it's not, but you know what? I'm looking at this and I'm willing to be convinced. You know, I don't think they've got enough there to say yes, we have this. But
and they're not saying that either. I know the researchers themselves are going back, asking for more time on the JWST to get some more longer exposures.
which
doing the
will
same
help with that
thing.
signal to noise
Yes,
ratio.
which will increase the signal to noise, beat down the noise more, and then hopefully be able to increase the confidence of the detection of these two types of molecules. But we'll have to wait and see on that. Obviously, that has to be approved first.
And I would like to make one more comment on that, and that is that though they may detect these here on Earth, these are signatures of biological activity.
Well, let's save that for the end here.
Okay.
Let's look a little bit.
I will hush then.
Yeah.
Okay.
Let's look a little bit more of the sort of the data itself.
Okay.
And I wanted to go to this slide here. So on this slide here, it actually shows you the confidence on the far right column of the detection using various combination of these modeled spectra that we looked at prior, and how you go about fitting, if you like, the spectra from these different molecules. And the thing to note is if you look on the far right column, the sigma values is the ones that we're interested in. They're all about 3 sigma.
Mm-hmm.
Okay, 3 sigma. So this is a 3 sigma detection. Now, in general in science, like let's say particle physics, if you were to discover the Robert Moore particle,
Woo!
it would have to be a 5 sigma detection.
And for
Because if you have a lower detection than that, lower significance of detection, it's hard to separate the bona fide detection from, random statistical fluctuation of the noise that happened to in that moment of time that you're observing come together and give you a high signal to noise, higher than you would expect on average. But then over the long term, it's not that out of norm when you think about it.
Right.
The probability of that occurring is not like 1 in a billion billion. If you do things enough times, it's going to happen on a fluctuating system like that. Statistically, that you're going to pick that up.
right.
So what we want to do is to observe or do the experiment long enough that you can beat down the statistical noise, if you like, so that any real detections would eventually show themselves. And as an example of that, after the Higgs particle was discovered many years ago by the Large Hadron Collider, one of the things they are trying to do after that is to look for other types of particles.
That are predicted by those models.
And there's some predicted by string theory, these supersymmetric particles, and looking for the dark matter particle and so on and so forth. And there was an indication of an observation in which looked like a particle was detected, but it was only around the 3 sigma level again. And this was based on a certain block of data where the instrument had run for a certain period of time. And they knew that they had more data that was coming in that they could add to the first batch. So when they were like, okay, there might be something here, they reported at the summer conferences that they have every year. We're going to look, keep a sharp eye on this region to see if there's anything there or not. But when the next block of data came in,
there was nothing
it
there.
went away. It was just a random fluctuation, you see.
Right.
So you got to be that's why we set that threshold at 5 sigma.
Now, these sigma, is that the same sigma as we talk about with Gaussian distributions? Okay,
Yeah.
because I'm going to mention there that plus or minus 1 sigma has 66%
Right.
of the values in it. So, when you go to plus or minus 2 sigma, you're now talking about 96%, if I'm remembering correctly.
Yeah, something
like that.
95 or something.
So when we're talking 5 sigma, you're talking about 99.999%
right.
certainty on this value. So, when they're talking 3 sigma, there's a good chance that that's a true signal, but it's not good enough. So
Yeah, you want it to go to 5 sigma if you can,
Yes.
because that's sort of the threshold that scientists have adopted.
right,
As a saying, there's something real here, and it minimizes the chance of being fooled.
right,
And that's what we're trying to prevent. You don't want to make a grand announcement and then have to bring it back later.
What you mean, like the press has done with this announcement?
Or cold fusion.
Yeah, our cold fusion.
Do you remember cold fusion?
I do. We've been 10 years away from that for the past 30 years.
Or the Bicep 2 team that said they discovered the polarization, remember,
Okay.
of the CMB, and it
Yeah,
gave support
yeah.
for the inflationary model.
Or there was that group that
And then
said, "Hey, we found magnetic monopoles," and just all kinds of things. And
Yeah, I mean, that happens a lot. Even dark matter, there's been cases where people have reported detection of dark matter particles in their detectors and so on and so forth. But yeah, so they turn out to weren't. Yeah, no one else has found the same thing, so that's a problem.
But the press gets a hold of things like this and blows them up and makes them sound
Right.
like, "Oh, scientists have found." No, we haven't. Not yet.
Here's the other thing when you're talking about sigmas and this stuff. You're assuming that the errors or uncertainties are Gaussian. Distributed.
Right.
What happens if they're non-Gaussian, right? Then
Well,
that's a different thing, you see.
that's a whole different bag.
But if you stick with Gaussian, then 1 sigma means that there's a 68% chance that your value that you measure is going to fall within plus or minus 1 sigma.
right,
Okay. If you're at 2 sigma, that probability increases to 95% that your measurement is going to fall within that plus or minus 2 sigma range.
right,
Okay. If you get to 3 sigma, that goes to 99.7%. But that doesn't, so this is what we're at here. 99.7%. But if those uncertainties are calculated correctly, that means there's a 99.7% chance that there is a detection of those molecules.
right,
Just think of that. By the time you get to 4 sigma, it's 99.994%. By the time you get to the fiducial standard of 5 sigma, there's a 99.99994% chance,
right,
that the measurement is correct, that there's something there. That's why we wait till we get to 5 sigma.
Yep.
That it's almost 100%, but just not quite.
Not quite.
But very, very, very close. That's assuming Gaussian statistics, of course.
Right.
We always got to remember that.
Could be shot noise. Could be Poisson.
Non-Gaussian random fields.
Right.
So you always have to be very careful and all of that stuff, if you like, the statistics. Now, it's going to take more observations to push this if it does reach 5 sigma.
Right.
But I think now it's fair to talk about what is the implications, assuming that further observations drive this to 5 sigma plus. What does this mean?
And I'm going to bring it back to us now.
Yeah.
What does this mean? Well, number one, this is a high Cyan world, so it's a water world with hydrogen atmosphere. We've detected the hydrogen through these spectroscopic means. How do we know it's ocean? Because there's water also been detected in its atmosphere. And due to its size and its density. How do we get size and density? Well, we know how big the star is, and we know how much of the light the planet blocks, so we can tell how big it is. And since it's where we can get radial velocity measurement, we can also tell how much mass it is. Mass divided by volume gives us density. So we know its density, and my guess is that it's probably right around 1, because 1 is water. So we can start making these types of conjectures about what it's like. But then the other thing about this is if it is DMS or DMDS is the detection, what's its levels got to be?
Right. That's what I was just going to point out. In order for us to see it, it has to be thousands of times more abundant than the same molecules here on the Earth. Thousands of times more abundant. In other words, if the Earth was at that distance, was orbiting that host star,
You wouldn't detect
we wouldn't have detected it. It would be too low of a level that the JWST would not be sensitive enough to see that.
Right.
So we know it has to. You can determine what is the abundance.
Which, I hate to say it, screams to me a non-biologic source.
Not necessarily.
Not necessarily,
Robert.
but
Let's be optimistic here. Number one, it's a watered world. Whereas what produces these molecules a lot of times? Plankton.
plankton.
What do you expect in a watered world? Lots
Plankton.
of plankton.
Right.
Now, whether they have tuna fish and you can eat them without dying, that's another thing. But the plankton will give off those molecules.
Mm-hmm.
And you have a very large planet. Like I said, it's several times larger than the Earth, on the order of about almost 9 times our mass and a little
Yeah.
over 2.5 times our size.
It's the warm Neptune, I think they call it.
Yeah.
Something like that?
Yeah, super Earth.
Super. I think it's a little bigger
These
than what's
terms are all
usually super, but these are not
Fuzzy. I mean, it doesn't,
defined terms.
never
yet.
get hooked on these terms, right? Just
Right.
give us the numbers. 8.6 times the Earth's mass.
Right.
And there's uncertainty, of course, on all these numbers here. And 2.6 times the Earth diameter.
Right.
So that gives you sort of perspective on this. Yeah, it could be a watered world, and it could be lots of
Lots of plankton.
blue-green algae.
Yeah. Oh well.
Do they make
Well,
this
there is
stuff?
CO2. There is CO2 in the atmosphere. So
There's CO2 in the atmosphere, and there's methane. So this type of life, now, it's a possible biosignature. In fact, there were reports or papers done over the last several years where people looked at this issue. What would be a good biosignature? Like, what would uniquely tell us that if we detect this molecule or atom, or it had to be a molecule, if we detect this chemical in the atmosphere, some exoplanet, that would almost guarantee 100% it has to be from biology. And this molecule is in this list.
Really?
It is.
Okay.
So
Because I got to admit, I can't think of a single one that this one alone would do it. But oxygen plus methane plus this stuff, I'm willing to bet that there is. But for it to be that high, I'm thinking there may be an.
now we talked about CFCs in the past.
CFCs.
So there's any type of industrial pollution.
Right.
But that's so Earth-centered thinking.
Right.
You try to get away from that, right? Who's to say there's any industrial revolution going on some planet? It just seems bizarre. But at the same time, at roughly, minus modulo the 124-year time difference for that light to get here from that planet, of course. But plankton or algae-like or any type of biology that's in the water itself could potentially give off this molecule. And maybe that is telling us this is our very first body in which we have a hint of possible life beyond the Earth.
Right.
And the cool thing about it, at least if you let's just to expand those points, okay? The cool thing about it is if we go to Mars and pick up some material and bring it back to our laboratory and we look at it and we find there's life. Let's say it's a bacteria that's dead, right?
Right.
Or it's still alive, but just bacterial type of life. Then you're always wondering, is that life that was somehow came from the Earth to Mars?
Right.
Because the Earth was bombarded, especially early on, by large rocks, right? Planetesimals.
Or did it go the other way?
Or did it go the other way? And so those, if the Earth got hit by something and there was already bacteria on the Earth, and those rocks get ejected into space, and inside those rocks, bacteria managed to survive, and then the Mars crossed the path of that rock, so the rock entered the atmosphere of Mars, landed on the surface, and then those bacteria found their way out of that rock into the rest of the soil on Mars. So, in other words, we brought over contamination, right? Panspermia. Idea,
Panspermia.
right? Or went the other way, as you suggested, right? Maybe Mars had life originally, and that came over to the Earth and contaminated us. But when you look at something like this, it's why it's exciting. It's 124 light years away.
We didn't do it.
So, our garbage is not on that planet. You see, that's totally independent from us.
Right.
So if there's life there, of course, getting there is going to be a real problem.
I'm not waiting on that trip.
But at least you have a target. You know where to go.
Yes.
So in the future, if we could get technology to the point where our spaceships can go up to a very high fraction of the speed of light.
That's where these ion thrusters come in, because it takes very little fuel and you can have that thrust
And
for
you,
centuries.
and you'd never send a human being.
Oh, Lord, no.
There was no reason why you should. That would actually slow everything up, the progress and how
Right.
long. You send AI controlled robots would go there
Right.
who don't need backup systems. They don't need air to breathe, or they don't need to drink water or eat food. All they need is energy
Right.
to live. You send that there to do all the exploration and then radio all that information, send it back to Earth.
Yep.
And you don't know, I mean, would you really go to a planet in which there might be life forms? Think about how would you interact with those life forms, right? Would you, there's no, if it's water and it's really deep, you lower a boat into the water somehow. And of course, the condition of the atmosphere is probably high pressure,
Right.
So then that would be hard for us to survive. So you end up sending probably robots down to the surface on the water anyways, and then have something like a little miniature sub that goes underwater, trying to, what would you do? Grab a sample of it? And would our morality be such that we're allowed to do that, capture a glass of water and take it off the planet, right? I mean, because you're taking life away. Do we have the right to do that?
Right.
Or should we analyze? You know, it's all kinds of questions you can think about. And what about the dangers involved, like germs?
Well, that's why you definitely wouldn't bring it back.
No, I mean, you don't know. You think COVID was bad, man.
Right.
You brought something like that. You just don't know what you're going to face, you see.
Right.
But the exciting thing is we know that life formed somewhere once.
And this would be twice.
Did it happen somewhere else?
Right.
And then it doesn't become like can I use the word, a fluke of nature?
Right.
That it happened here. All the conditions had to be right. It's like the rare earth idea.
Right.
All the conditions had to be exactly right in order for life to arise. Of course, in that case, they think more of intelligent life. But in bacterial life, is there more than one place that's far enough away from the earth that we didn't do it?
Right.
And that life independently, put it that way, independently arose.
Yeah.
And I would say the reason, of course, as a scientist, you look at the statistics, the probability of stuff, right? And you say the probability seems great. Why? Because you have all the basic building blocks. We've observed nearly 300 different molecules in space, in the interstellar medium, using our radio telescope. All kinds of different, there's lists of them on the internet that you can look at.
Including several different types of amino acids and everything.
And all of the basic
All
sort
the
of
things you
structure
need.
about DNA and RNA.
Right.
So it seems like everything is there out in space. Is whether it came together in the right way, and we don't know what that right way is, so we can't say it. Right? We don't know how you go from non-living to living. Did it come together in the right way to produce biology somewhere else? And this may be our first example of evidence of that.
Of biology. Yeah. I am hoping to eat this plate of crow. Okay. Do not get me wrong. I'm sitting here sounding like the naysayer and the one who wants to rain on the parade, and I am to a degree, but there's a certain level of extraordinary claims require extraordinary evidence. So all of these things need to come together, but I will happily feast on that plate of crow, and say, yep, it's life out there.
Wouldn't it be amazing if that was the biggest thing that revolutionized our thinking as a human species with the James Webb Space Telescope was the detection of the biosignature in some
the first
exoplanet.
one. Yeah.
The first one.
We do have a question. Mizuho or Bill Schwam is asking, how would the huge gravity? I'm not really sure what you're asking there. If you're asking how large the gravity of this world would be,
Affect biology. Yeah.
I mean, huge gravity would affect biology of things there. Absolutely.
Yeah, and think about the structure. That would affect the actual structure design of the critters.
Right.
Imagine if they needed to propel themselves through an ocean, right? So they would have better ways of doing it than what they would on Earth. A lot stronger. And the other thing, maybe they hug the bottom. How do we know that? Maybe there are vents, geothermal events at the bottom of the ocean, and they live off of that.
Well, the neat thing is here's an interesting thing to think of, is if depending on how deep the ocean is, how much pressure you get with that level of gravity, the ocean bottom could actually have a line of this form of ice that's almost a gel. Because, we're used to this, I think it's type 4 ice. That's the 32 degrees that we experience in North Dakota all the time. But there are other types of ice. There are other phases of ice. We've discussed them, that some are as hard as rock.
Right.
And there is a type of ice that under that much pressure forms. And so it's warm comparatively, but it's there.
Yeah, it'd be interesting to know what is the heating at the bottom of some kind of planet-wide ocean.
Right.
Is it geothermal, so it's actually warm, quite hot?
Right.
Is there nutrients that come up from deep in the interior of the planet that these algae feast on?
Yeah.
And obviously the molecules have to make their way to the atmosphere, so they percolate upwards and get released from the top of the water, the ocean.
That would be the interesting thing is with it having a hydrogen atmosphere, would things tend to float and percolate up instead of falling down?
Well, and the other thing is the hydrogen's not going to escape like it would here because gravity can hold on to the hydrogen more so than the Earth, obviously.
Just all kinds
So
of
the
neat
escape
things.
velocity is going to be a lot greater, obviously, right?
This if there were intelligent life forms on this planet, it's almost certainly they're not developing a rocket program.
Yes.
You know,
That's
because
the
the
other
gravity is too high, they would not be able to get out of that gravity well with any chemical propellant.
Yeah, that's the other thing. We happen to live on a planet it's almost like the Goldilocks planet. It's
Right.
just right in the sense that we can leave the surface of the Earth with technology that is not too advanced,
Right.
that we'd never be able to develop it.
And look up, for those of you interested, it's called the tyranny of the rocket equation. There is a limit on how much thrust you can get from chemical propellants. And so they would have had to have developed a rocketry on this world of a different sort than what we did to get off the planet.
Yeah.
So
Would you expect intelligent life like us, technological abilities, to live on a planet like this?
and that's the question, isn't it?
I mean, based on everything we know, the answer would be no.
Right.
At least it'd be very low probability. So chances are it's just a sort of
Yeah. But
yeah.
biology of any sort is just absolutely cool.
Just knowing that happened somewhere else.
Right. Now we got a sample size of 2.
Yeah. And then of course that increases the odds we're going to find it again and again and again and again and again.
Right.
If it happened one place, okay, you could say it was a fluke. If we find it in another place,
Now
it's only 124 light years away.
Right.
Given that the diameter of our own Milky Way, just our galaxy alone, is 100,000 light years. So that's a huge volume of space to probe.
With what, 10 billion stars?
Yeah, so on the order upwards to 400 billion stars.
Right.
Because most of them are low mass stars. There's
Oh, right.
a ton of
Good
those
point.
out there, right?
So,
Yeah, so there's a lot of places to explore.
right. And we need to keep doing it.
Need to build
that's
the
one
instrument.
of the biggest things that makes us human is wanting to explore.
Yeah, you got to build the instrumentation, though, right?
Absolutely.
You know, you don't need to go there to look, right? You can build telescopes that allow you to do the probing from Earth.
Would be fun to go, but we need to advance significantly from what we can do right now.
You got that right. A lot of engineering needs to be
Lot
done
of
between
engineering.
now and then, for
Yep.
sure.
So
Yeah, but this is interesting. So stay tuned.
stay tuned. Hopefully we'll be
Well, I'm hoping that,
revisiting this.
you know, if I was on the time allocation committee for JWST, and if they wanted to get additional observing time to increase that signal to noise to make it a 5 sigma detection, why not?
I'd be
It's worth it.
I would be considering it strongly. Yeah.
I'm sure they are. I mean, they're
Yeah.
they're scientists that know what they're doing, so they'll do the right thing here. So we'll stand by. Maybe in about a year or so, a year and a half from now, we'll get exciting news that this is actual detection. But then the argument is this, Robert. Before we get off of this
Okay.
topic, the argument then becomes this: is those molecules produced by abiotic processes?
That's kind of what I was
Okay.
getting at. Yeah.
And it turns out that there needs to be more work done in the laboratory to really go into that further. There actually hasn't been a lot of work done in these chemical reactions involving these molecules to see if they can be produced abiotically.
Right.
And so I think if nothing else,
Well, that's why I was trying to point out that there almost certainly is not any one molecule that says, hey, there's life there. But when you start getting combinations of these molecules, oxygen, methane, all these molecules that do not last long in an atmosphere if they're not being replenished, and you get several combinations that are not replenished by the same process, now you're starting to go, except life.
right?
Now you're starting to go, you're getting to that 5 sigma on, is there life here?
It's becoming interesting, right?
Right.
So we could hit 5 sigma, but not produced by biology.
Right.
That's the thing. And so I think we need time for the chemists to look
to
at this
really
in
work at
detail,
this.
to see if this really makes sense, if there's really something there. Because it may turn out to be not a really good biosignature to begin with, because it can be produced non-biological activity. And that would be unfortunate.
It would be unfortunate to say it was biological activity and then 5 years later have to come back and go, oops.
I mean, what else would you use besides this? We said CFCs, but that's like an industrial civilization.
Right.
What happens if microbial, life forms or algae-based life forms are not going to produce the CFCs?
No, they're
So
not.
is there any other way that we could use to detect life? I don't think so.
I don't think so
They can
immediately.
all be tied into non-biological activity that produces it.
Right.
And that's where you're talking about in situ type of measurements, right?
Right.
Actually go there, right, and explore, take samples and analyze it to look for signs of life.
And I got to admit, I think as long as we're not taking anything with us, it's okay to sample.
Just the prime directive from...
I mean, if we find that there's intelligent life there, I think we need to back off and say that's their world,
Well, like we see in
But-
sci-fi shows and movies, right? Number one, you don't want to upset the apple cart.
Right,
And we could contaminate things not knowing.
right.
So that's
But-
always a problem.
At the same time, I want to see the microbe that even if it insists is going to survive the tens of thousands of years to get from here to 124 light years away.
Thinking about Christopher Columbus,
Yeah,
it's not like he knew he was dragging germs from Europe in the 1400s and going to kill people in North
not
America,
wrong.
right? He didn't know that.
right.
But that's the unintended consequence of his exploration.
But you know what we can detect from orbit?
What?
Bioluminescence.
Right.
All of these other factors of
Yeah,
biology.
we could do it. And then we
still-
can decontaminate things as well.
you see, I agree with Bill.
Yeah,
Let's
he wants to
boldly go. Absolutely. Let's get there. Then we can decide
Be
on
a
the
cowboy,
morality.
stick a popsicle stick in the mud that has green slime in it and give it a little taste.
I don't know about that, but
You go first, Robert.
yeah, let's boldly go. Let's find out if there's likely something there, and then figure out maybe how we can get some of our autonomous systems there.
But there is a lot of weird exoplanets. The more we detect, we detected
The more we detect.
thousands and thousands and thousands of these. There's well over 5,000 now, I think, the latest count.
Yep.
And
some in situations where we would thought, no, this can't happen.
yeah, and there's a good example of that
Right.
we've picked up on the news lately. And this is
This is it.
So this object, okay, so first of all, what are we looking at? So the image on the left is taken from the DESI survey. That's the one that came out, remember we talked about the other week, where it's possible that the dark energy changes with time.
Right.
So the strength, if you like, of the dark energy from day one, the beginning of the universe, compared to today and all the intermediate times, is not constant. It's actually changing. And if there's some time evolution in the dark energy, then this actually puts some constraints on some of the models of the attempts to explain what dark energy actually is. So an image taken from that survey, just serendipitously, photographed a binary brown dwarfs. So these are two objects. So what's a brown dwarf? Robert, do you want to take the
Sure.
lead on that one?
Brown dwarfs are simply failed stars. They may have had enough mass that deuterium, so a hydrogen atom with not just the one proton, but also with a neutron on it, deuterium fuses a lot more readily than regular hydrogen. So they may have had enough mass to actually fuse deuterium, but that is not a stable reaction. That will not produce a star. So these are failed stars. They have too small a mass to fuse hydrogen steadily. And there's different classes of them depending on how much mass they are, and I don't have the records to be able to say what type these are. That's what I'm saying they may have. But it's a binary system of two brown dwarfs. From this picture on the left, I'm thinking there may be a third component of it.
Yeah, so what you're seeing here is that the two of them, which is 2M1510AB. AB is the two binary brown
binary,
dwarfs
yeah.
in this case that we're looking at. Now, The brown dwarf would have a mass, I don't know if you said it or not, less than 8% of the sun's mass.
Right. So less than 0.08 solar mass.
Yeah, it has to have a mass at least that and greater in order to have sustained nuclear fusion in its core of hydrogen and helium. So this is the case where we have two brown dwarfs that are in orbit around each other, and that comes from radial velocity measurements of the system. And these are done with the Very Large Telescope in Chile, the European Southern Observatory. And what they discovered is that there is a planet that's in this system. And this planet is on an orbit that's highly inclined, almost 90 degrees. In fact, it's in a polar type of planet where it goes up and down, if you like, the plane of the orbit of the two brown dwarfs. So if you think of two brown dwarfs orbiting in a disk, this planet orbits in such a way that it goes above the disk and then down below the disk and then above again, continuously.
Which does not surprise me. This would be a gravitationally unstable environment, so it would tend to be thrown to high inclination.
Yeah, so this is a really weird discovery. So this was published recently. Here is the title page of the paper itself. So the planet is very close to being at that 90-degree point, where it's a perfectly polar orbit that would be in around the center mass of the binary brown dwarfs. And I don't think anything's been found like that. Number one, they're very difficult, right? Mm-hmm. So for planets going around binary stars or objects,
right,
there's only about 16 of them known at the present. So out of over almost 6,000, only 16. Very rare in that sense, right?
You got to remember that a star alone is a massive object, so it churns up a lot of gravitational force. When you got two stars orbiting each other, stuff gets very unstable very quickly in the nearby environment.
But that orbit, that polar orbit of orbiting at an inclination of 90 degrees with respect to the plane of the other two objects is stable enough. That's a stable orbit.
Yes.
Right?
Because it's not being tugged by one more than the other.
But, the chance of being there is fairly low, put it that way.
Right.
Could you make the analogy of balancing a pencil on its lead?
Yes, that would actually be a very good analogy.
That's sort of. Anyways, this is the first case of a planet that's been found like this in a nearly 90-degree orbit.
I still remember how floored people were when they found planets around a star in a binary, because that was thought to be impossible. Then they found planets going in orbits around the binary. So Tatooine, essentially.
Yeah.
And that was thought to be impossible. And it's because of this gravitationally turbulent environment of when you have two massive objects circling each other, it tends to scatter anything that's nearby.
Now, if you go to the next slide, you'll actually see a breakdown of some of the orbital parameters. So here's some of the information about the planet itself. So let's say it takes about 21 days to go around once. Its eccentricity, so how squashed or circular the orbit is on the order of 0.36.
So very elliptical.
Yeah, so it's not a circle at all, not a circular orbit. The interesting thing is the inclination angle, 88.5 degrees plus or minus 0.1. So that's nearly 90 degrees. You're really, really close to that 90-degree limit. So that's very, very interesting. So... Yeah, and it makes you think that since it's not exactly 90, there's an uncertainty in here. I don't know if the 0.1 is actually a good measurement of the total uncertainty, both the random and systematic uncertainty.
Yeah.
But if it's off a little, if there's some perturbations in the system, will the planet's inclination migrate around, let's say, 80.5 to you're 1.5 degrees on one side of 90, and then it slowly evolves over to the other side and then brought back in again. So you got this kind of, family of orbits which have this small range of inclination to describe them, centered on that 90-degree position. That would be interesting. You could model that, of course. Right?
Yes, you could. And you could model how much of a perturbation it would take to do it.
Yeah.
Now, Bill is asking a question, what makes the two bright objects orbit at different centers? So I think he's talking about this image, the blue rings. Why are they off-center like that? Because they should be orbiting their common barycenter.
Yeah.
So they should be like dance partners holding arms. with each other.
Yeah, that there I think is based on the uncertainty in that as well.
Okay.
So there's an uncertainty in the tilt of those orbits. You know,
So-
they all have that, but they're both of them orbiting the center of mass of the system itself.
Right. So I think it's a problem possibly with the artist's conception of this type of system
Yeah.
as well. I'd have to dig a little more to do it. It could also be something I'm noticing 2M1510C, which says that there's a third component, probably
But
another
that's
brown
quite
dwarf.
a lot further away.
But it's a lot further away.
Yeah, so it's not going to have that type of an impact. And
Right.
a lot like perturbations on the system itself.
Okay.
Yeah.
So
And the other thing is, you think of conservation of angular momentum, there's no reason why they would go out of the plane of the orbit like that, right? And the exoplanet itself will have a tug on those planets
on
too,
those
of
two
perturbation.
stars. Yeah. Because when you're talking about these brown dwarfs, you're talking about something that can be as small as 20 Jupiter masses, 20 times the mass of Jupiter. So comparatively, they're not much bigger than this planet.
Right. Actually, if you read the abstract, they mention the fact that the precession that you see in those orbits is due to the exoplanet itself,
Okay.
the polar planet. So that's the perturbation that gives rise. And they're trying. I think they're making it more so than what it would be.
Right.
And
They're
but
exaggerating it.
Yeah, and you wouldn't be able to see
Pardon.
it otherwise, right? It'd be such a small angle
Right.
that you'd never notice the difference. So the artist's conception here is emphasizing that angle, but the perturbation is from the exoplanet.
Yeah.
In fact, it is in their abstract. that they
It's just,
describe
I don't
that.
know. I think I agree with, I'm imagining it was Bill asked the question. I don't imagine that they're actually the two major components of the system are in that figure 8 configuration. They're almost certainly orbiting in a little more standard of an orbit. Yet, like I said, those dancers holding hands and
Right. Yeah, and all of that, the orbital tracing depends on how you look at it, right?
that's true too. Yes.
That way when you think about it.
But yeah, the objects orbit their common center of mass, so it would be very unusual to see it as two links of chain like that.
Right. Okay, so anyways, we'll see how but that's only one out of all those planets that was like that. So there's got to be more out there, just exceedingly rare.
Yeah, and for all the reasons we discussed. So
yeah, for sure. Well, if you're interested in that, if you wanted to dive into what makes orbits, the science behind the orbits themselves,
or how we get to this planet to sniff its atmosphere with the real in situ sensor.
How do we come up with the different orbits of these planets?
Yeah.
Just by taking observations, radio velocity measurements. That's interesting in its own right in that sense, right?
Right.
So all of this involves education.
Right.
To learn this. And places you can go, including, of course, University of North Dakota, both on-campus courses and online courses, as we always like to say nowadays, depending on your situation, whatever fits your needs.
Right.
We are here to help.
That's
We
it.
have programs in both math and physics and
Computer science
computer
and
science
engineering.
and the arts and you name it. So
Yep.
everything going on here right now. And of course, now we're at a time of the year where the semester's starting to wind down. You notice that, Robert?
I have, and you can
people
tell
are
by the students too.
They're scrambling to finish up their last minute things, and some of them will be graduating very soon in a couple of weeks, and final exams will be starting soon as well. And before you know it, it'll be all over. And
All
a
over.
new crop will come in the fall.
Woo!
What was that saying?
Actually, I'm like seeing new
that
students.
Matthew McConaughey used to say? He goes, every year the students are to say that I get older and the students stay the same age.
Right. I feel that.
Yeah, exactly. Okay, so if you'd like to join us on our next podcast, it'll be next Tuesday on April the 29th. The thing that we do, of course, at the end of all podcasts is to
Give a quote.
give a quote.
So
And this quote is from Carl Sagan.
I was expecting him.
You were.
I was.
You know
With
me
all
too
of this
well.
about life and other planets,
That's
who else are you going to quote?
That's the tie-in. Now, I didn't want to give his standard quote. What's this quote that everyone says all the time about this kind of stuff? Extraordinary.
Extraordinary claims require extraordinary evidence. I even said it earlier myself.
Yeah, and that's not the quote I have today.
Okay.
But that's what he's really famous for. It's probably
Yep.
his most famous quote. So the one I have today is this one. Quote, "It is far better to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring."
That's it.
That's it. And
All
if
right.
you like this podcast,
Give us a thumbs up.
you give us a thumbs up. If you haven't subscribed, please consider subscribing. And we'll see you next time. Thanks for watching.
See you next time, folks.